in the second part, today, we now go from smaller statically determinate systems into the full cable stayed bridge, and to understand what we learned in the first lecture, how it applies to complete cable stayed bridges. We talk again the permanent loads. I tell you, the heart of cable stayed bridge design, understanding of calculations are the permanent load stage. Everything else is simple. But permanent loads, you must understand why we do it the way I show you. Then, of course, we talk about transient life loads. We talk about stress influence lines called, I use then current point moments for that. I hope you know all about that. I'm not going in great detail, but we need it here. Then we show again the nonlinear effects for the full bridge, which I showed you the basics, the approximations. We then superimpose the life loads on the permanent loads and talk about temperature loadings for cable stayed bridges and the hand calculation of eigenfrequencies of cable stayed bridges, which we need for the preliminary calculation of aerodynamic stability flutter. Okay, permanent loads. I've shown you the cutout beam and said rigid supports so that it doesn't run away. Now, how do we achieve for a true cable stayed bridge this rigid supports? Because the cable stayed bridge is supported by elastic cables. Well, the secret is the loading permanent loads for a cable stayed bridge consists of two parts. The first part, we have here a simplified system, is when we place the dead load onto the real elastic system, and then we get a run of moments like this. Understood, huh? And now comes the trick. We apply a second loading, which I call cable shortening. We give the command to the computer, shorten the cables by a certain amount. And then we define the cable shortenings in such way that we end up with a run of moments which is identical with those moments we would achieve if we would have a rigid support here at the cable anchor point. Again, the rigid support. So, on site, where we have only elastic cables, we achieve our desired run of moments similar to those of a rigidly supported beam by applying, first of all, the dead load to the true elastic system by computer for the fold system. We get a run of moment, and then we apply a second set of cable shortenings which give us an additional run of moments, and those together, dead load on the elastic system plus cable shortening, gives us the permanent loads. You understand, we have dead load, we have cable shortenings, and we have the permanent loads, and they have the two components. That is the heart of the design of cable stayed bridges for permanent loads. Remember. Now, what moments do we want to achieve when we apply the cable shortenings? I mentioned already, for the concrete beam, we know we want these QL squared 12. It's as simple as that, rigidly supported beam. And for a steel beam, we choose something for a minimum of material. Next time, in the numerical calculations, I will show you how we arrive at the set of cable shortenings, but we define that's the moments we want, and then we have given the moments dead load on elastic system. So we can vary, or we can then apply the cable shortenings with the computer in such way that the sum of elastic and cable shortening gives us the desired run of moments in the final for permanent load. Well, a little bit back, I mean, you know all that, but just the statical theory behind that a little bit. We have here a base system, which is statically indeterminate. By first approximation, the cables are the statically indeterminate. If we look into it, the statically determined system is the one, the full beam on supports, between the abutments, but no supports. So we have 4, 5, 6 stay cables, which are statically indeterminate, plus the pier support. Those are our statically indeterminate. We can cut the cables and remove the support. So we have a system with 7 statically unknowns. And now, as we all know, we can choose freely as many action forces or geometry as we have statically indeterminates. We have 7 here, so we can choose. Now it's appropriate to choose for the right-hand side those which are closely related to the statically unknowns. Okay, related to the cables are the beam moments. So we choose here the beam moments. Then related to the support, of course, is the beam moment at the support. And finally we have one free, thank God, the 7, and that we use to determine the tower moment. So, with this set of statically indeterminate ones, we can define all beam moments. I tell you, use the beam on rigidly supported supports, beam rigidly supported, plus the tower moment. That is behind when you say, well, you choose. Yes, I can. I choose as many indeterminate statically as I have statically unknowns, and for that I use the moment. You can use others, but that's the simplest. Again, an example, Posadas. This is the run of moments for the dead load on the true elastic system. Big moments. We have here this run because we don't have a support here at the tower. All the beam is completely supported by the stay cable. This is a tower moment. And now, this is now the run of moment I choose to achieve with shortening all the cables and the tower moment. And if I superimpose then the dead load on the elastic system plus the cable shortenings, alas, I come to the moments of the beam on rigid supports, because that's what I have defined. I define this as a result, and from this and this I calculate a set of cable shortenings to achieve that. Every cable stayed bridge is designed in such way. It's not much spoken about because only few people know what's really behind, but that's what it is. That's the secret of the cable stayed bridge design here. Because that the computer does not deliver you. You have to tell him what cable shortenings to apply. He gives you the life load moments, you put it on, run through, but this you have to tell it a little bit more to the computer. Okay. We spoke about concrete bridges where I say beam on rigid supports, and we see here's an example, Pesco-Kennewick. These are the beam moments under permanent loads, chosen those rigidly supported at the stay cables. And these are just the normal forces consisting of the normal forces from cable inclination plus the additional post-tensioning here where we have little normal forces. That's how a realistic bridge looks. Steel bridge is a little bit different. We see here, this is the run-of-moment dead load on elastic system. And these are the moments from cable shortening. And the sum, permanent load moments, are not exactly those of a rigidly supported beam. We can do that because these do not creep away, and these moments, the permanent load moments, together with the life load moments, give the minimum amount of steel for the beam. They are normally for steel bridges negatively because on top of the steel bridge we have the orthotropic deck, which by itself is wide and strong, and the bottom flange is rather small and thin. So cable-stayed steel bridges are normally not beam on rigid supports, but normally have a negative permanent load situation because that they can take more life load plus this in the top flange. Same for the towers. We can, by pulling at the cable, say that we use the forestays for the beam and the backstays for the tower, have sufficient statically indeterminate units. So this is the run of moments under permanent loads. It's FLE, which is on supports here. These are the moments due to cable shortening. Oh, beautiful. And under permanent load, there's virtually nothing left. So then we have to superimpose the life load plus minus with this to size the tower. But the basic principle also for the tower, we take out the dead load moment from the elastic system by appropriate cable shortenings. Just the same. Very briefly, to give you an idea how the run of moments of a real cable-stayed bridge goes, if we load it fully, then we have, of course, the big positive moment here in the bridge center. We have supports here, so we have negative moments here. If we just load the center span, we have the same more or less positive moment as we have here, but the side span moments, which are pushed back, so to say, by these, there are no loads, so they, from this loading, they just keep up and are pulled back by the anchor pier. If we load, this is better here. So if we load the center span, we have the big positive beam moments here, and that goes on until here the beam is pulled back. Here you can always think of curvature. We have a positive curvature, clear, in the center, so big positive moment. And we have a negative curvature here, so we must have negative moments. I think it's easy to understand. If we load the side span, on the other hand, then we have here the big positive moment, sagging of the beam, and there's nothing here, so it's a negative here, and then it tapers out. This is something in between. If we now look at influence lines, which show us how much a moment at a given place becomes if I place a load somewhere else, then we see here, if we want the moment, member 9, no, 2 left is here the beam moment at the support. Okay, typical negative influence line, we have to load closely to the tower here, and it gives us a big negative moment on top of the support, and that goes through all typical action forces. In a preliminary calculation, we normally just calculate this moment here. We will see it next time how to do that. And then we can, however, from this moment deduct the complete run of moments. That's the moment envelope, of course. It decreases here more or less if we have a support. And here, because we have a rigid support here, it's a little bit bigger even than here. And the negative are only 40% of this, and so on. So with one moment, that's a typical run of moments for a cable-stayed bridge. Moment, life load, moment envelope. Permanent load, we know, rigidly supported. These are life load envelopes. Now, current point moments, I'm not really going into because I think you've learned all that. The problem sometimes is if a load creates moments and at the same time normal forces, then we do not exactly know what load position gives us the biggest stresses. It's typical for an arch. If I load the beam of an arch, I get compression, of course, in the arch itself, and I get bending. And then, when I get both, it's not clear what is the correct load position. Same is true for a cable-stayed bridge, of course. With a load, we create in the beam at the same time normal force and bending moment, with each having different influence lines. And so, where do we get the biggest stresses? So, actually what we are after is to find stress influence lines for top and bottom. We know moment influence line, normal force influence lines, and what we can do is we can use so-called current point moments. Well, we all know if we have a beam with a normal force and a moment in the cross-section, the stresses are clear. Now, if we shift the normal force, or if we have an eccentric normal force, then we get stresses from a central normal force plus the moment N from the shifted force times Z gives this. So if we superimpose that, we get this run of stresses. And if we now say, okay, my governing position of this normal force is that where on the one side the stress becomes zero, and on the other side, well, some logically maximum stress, then we call this distance what is called here Z, or Z in American, we call the Kern width, which gives us zero stress at one time and the maximum stress at the other side. And so this Kern width we call K upwards or downwards. And to cut a long story short, we have to combine the influence lines, moment influence line plus normal force influence line multiplied with a K, reduced. And the sum of these two influence lines, moment plus K normal force influence line, that's what's said here in the very end, that gives us the governing load position for the biggest stress at a given location. For example, the footing of a tower, if we have the regular box tower with a certain width, the moment influence line looks like this. Mechanism, turn, you know all about that. Okay, so if I want to get the biggest plus moment, so to say, I have to load this span. If I want to get the biggest moment the other way around, I have to load this span. That's easy. Now the normal force influence line, of course, I have to cut the tower, move it up by 1, and then I get the deformation here gives me the influence line. We see very clearly we need full load. So we have different influence lines for the moments here, that's half-half, and the normal force. What is the position, or say the extent, of the uniformly distributed load, the load package, which gives us the highest stresses? Well, I show you an example here for a cable-stayed bridge. We have here the load package. We are looking for this tower moment. Tower is fixed to the beam. We look to this moment. And the influence line for this moment is the full line. And we have differences in 0. And the load package, for that, we have to load this, or this to get the biggest positive moment. Now, if we look into the kern point moments, then we find, the way I've told you, if we superimpose moment influence line plus k times normal force influence line, a partial influence line, depends on the relation between section modulus, what we call W in German, S in English, Widerstandsmoment, to area. Well, you know all that. Anyway, you see here that we have definitely different extents of loaded length to get max M, max N, or to get maximum stresses. Okay, then we have a few non-linear effects. What I tell you now is also important for you to understand. I mean, the computer does it automatically, but normally people don't know what they are talking about. And that is, how is the increase of stresses for a cable-stayed bridge beam created? You remember I gave you the example, elastically supported beam, compression, buckling, and then the 1 minus n divided by buckling stress increase. But what happens? What's the internal run of forces? Well, there are interesting enough two phenomena which work against one another. And that may be the reason why we can build these slender cable-stayed bridges. The following happens. We have here an original stay cable, tower beam. And now we have a load on here. The beam deflects. The beam anchor points runs to here. Tower runs to here. And we have now two phenomena which create additional moments due to nonlinear theory, second order P delta effect. We have an increase of moments because of the, say, shifting of the normal force in the beam. If I have a load, the beam shifts down, bigger lever arm, bigger moment. That's okay, what we expect. That's the regular reason for an increase, nonlinear increase of a compression member, deflection, movement of the normal force, additional moment. But we have a second effect in a cable-stayed bridge which helps. And that is, when I move down the cable anchor point, the cable becomes steeper. And when the cable becomes steeper, it carries more of the load up to the tower, and thereby reducing the normal force in the beam. And that's what it's all said here, but that's what here really happens. So we have the two effects: shifting of the normal force, increase of moment. And we have, at the same time, the cable is steeper. Well, this is fixed, you have to say so. And by that, it unloads the beam. And these two effects work against one another. The shifting of the normal force is governing, but it's not as big as it would be without the steeper cables. That you should remember. Thank God for the second part, otherwise we couldn't do these nice slender bridge beams. We can also, I'm not going into that, assume the increase as a geometrical sequence, but those were old calculation tricks. I used them long ago. You're not interested in them anymore. Now, we look at some examples of increase of moment in the beam due to theory of second order, and we find that the increase depends strongly on the slenderness of the beam. If you remember backwards what I showed you this first hour today, where I said the more slender the beam, the more it can buckle and then go from buckling to stress increase, that's shown here. The Rhine River bridges, Mannheim-Ludwigshafen has a slenderness of beam depths to main span in the range of 60. These are the increases in current point moments. Basically, the increase is less than 2%. Well, good enough for bridge work. It's not worth to all that difficult calculations for 2%, isn't it? Okay, now if we go to something more slender, and that's typical for all the Rhine River bridges. They are in the range, people make strong, heavy box girders and good enough. Now, some others, like myself, said, no, we can. I showed you the stress is independent of the depth. Let's reduce the wind. However, we must pay the price in second order. Okay. Now, we go to the Houston Ship Channel crossing in Baytown in the US, which I showed to you. We have, first of all, not a box, but an open grid cross-section with a slenderness of 1 in 180 depths to span. Well, these are the increases in moments. We look at service load. They are in the range of 20%. That's 10 times the 2% we had at 1 to 70 at the Rhine River bridges. And if we are then really daring and do something like the Helgeland Bridge in Norway, which I mentioned, and I will give a special lecture on that, an extremely slender, daring bridge. That thing has a slenderness of 1 in 354, 1.2 meter depth for 425 meter main span. Now there we have, under service load, 30% increase in life load, and if we go to ultimate, we come to 50%. So that's about the limit. You can't go more slender because of the second order theory. But we had strong winds there. We wanted to reduce the wind loads. And now you understand much better the interwoven thoughts about beam depth, which is an important point to design, also from a statical point of view, a bridge. But when you do that, you must always have these considerations of second order and so on in the back of your mind. Okay, if we superimpose the permanent loads, here we see the elastic, the dead load on the elastic system. There's a tower support. Here we see the shortenings, and okay, it's a steel bridge. That is the permanent load situation. And if we now superimpose the life load envelopes with the permanent loads, then we come to something very roughly reminding you on the run of moments I've shown you. We get here these typical run of moments for a cable stayed bridge. Look here at the difference between first order and second order. I forgot, but the slenderness is not it's not very slender, the bridge. So we can see here from the difference in maximum moments for regular cable stayed bridge, there's not much increase. Same with the tower. In total, the permanent loads become to 0. And now another loading temperature, transient load, of course, on the elastic system. And there I have used a concrete bridge. In the scripts are steel bridges also. And typical loadings are the overall change of temperature. We have a base average temperature, which in Germany and many others is 10 degrees. And against those, we have a rise and fall of overall temperature between, say, plus 25 and minus 30, depends on the location. Then, if the sun radiates, the cables very often heat up faster than the beam. So we have there plus 15. That's one of the reasons why we try to get the white color around the otherwise black PE cables. I mentioned to you the black PE cables would be much hotter than if we have a white surface. We would have then to change this loading. Then the sun shines on the beam, the top of the beam is warmer than the bottom or other way around, and the sun is radiating from south, so the north side of the tower is cooler than the south side. So these are the temperature conditions, and then we can combine them to something we like to call summer morning or a summer storm or a winter morning or a winter night to get these combinations. And the run of moments, the envelope of temperature moments is like this. For service, it's not really important. It's additional load case, and in ultimate, they disappear anyway, but we have to take them for service into account. Finally, as I told you, if we want to calculate the important safety against flutter, which is a phenomenon I will tell you in great detail in January in the lecture, but it's what Tacoma took down, roughly speaking, this wobbling. And we can calculate that roughly, but we need for that the eigenfrequencies. And it's simple to calculate the rough eigenfrequencies of a cable stayed bridge. The bending frequency is 0.58 divided by the square root of delta, with delta being this deflection. That's an analogy to a simply supported beam, but it's good enough. There's only one trick. First of all, we calculate. It is always for eigenfrequencies. It doesn't depend what system there is, beam, continuous girder or so. By placing the dead load on the system and calculating the deflection from the dead load, and the bigger the deflection is, the more time it takes. I'm just not talking about F and T. If it's very stiff, it oscillates very quickly. You have a little deflection under permanent loads. If it's soft, weak, then you get a big deflection under permanent loads, and it takes time. Okay, and that's what this here is. So we load the bridge with its dead weight. However, there's a little trick. which is very often overlooked. The dead weight has to be applied in the direction of the deflection. Now, the deflection curve obviously is like this. So in the main span, we put the dead load down here. But in the side span, it goes up. So we have to put the dead load upwards. And I must say, even in my office, many years ago, when we still did this from hand, it was always done wrong. Until I found out. Okay, so with delta, the bending is a constant divided by the square root of delta. And then the torsion, which is maybe even more important for aerodynamic stability, the torsional frequency. Well, if we have an open cross-section, we neglect the small IT torsional stiffness, torsional inertia. We just do as if only the two outer cable planes act as a couple and keep the beam from, collapsing. And if we have a box girder, then we neglect the support of the two outer cable planes. These are approximations always. And just calculate as if we have a central cable plane only. It's about right. So with these very simple formulas, we can calculate by hand the bending and torsional eigenfrequencies, and then using an approximation, Klöpel-Thiele, I'll show you next time, to calculate the critical wind speed by which the thing can oscillate with a few helps. So, with this, I've told you what you should know about the flow of forces in a cable stay bridge in order to be able to understand what you're dealing with. It's really the understanding of it. I'm not very optimistic that you will really do a check by hand. My engineers don't do it anymore. And when I say, we do it in the computer, it's much faster. We can iterate, I know, yes, okay. But, so I'm not really thinking you need that to earn your money, but to do the calculations by hand. Although you will see next time, it's very simple. But what I insist is that you understand the flow of forces. And for example, this increase of second order beam moments in connection with the depths, because that goes in the very first try of the design when you say, what depths, let's make it slender. You must know what the consequences are. So in order to understand stay cables, it is absolutely necessary that you understand these very basic considerations of the flow of forces. The most tricky, I know, is to understand the permanent load situation. Make yourself aware that we have two loadings. Dead load on the elastic system, computer gives that. And then we define. We want, under permanent loads, this run, say, rigidly supported. And then you tell the computer, give me a set of cable forces. Give me a set of cable shortenings, which in effect, if added to the dead load on elastic system, give me this run of moments on the elastic on rigid supports. That's what the computer gives that to you, but and you can come there by iteration and all sorts of things. But I expect you to understand that. In the examination, we'll have 20 minutes of general questions, tower shapes and arrangement of cables and things like that. And 40 minutes are for calculation. And you will get a simple calculation task of what I show you tomorrow, of a preliminary calculation of stay cables or beam moments or tower moments or things like that. So that is the way we must have something to calculate in the examinations, and that will be this basic system. Of course, I'll make a repetitorium after the last lecture before the examination, where we will repeat all these things which can occur in the examination. So don't worry. All your colleagues before did it very nicely. But it will come up in the examination a simple calculation in the way on the basis I've shown you today, and practical examples next time. Thank you.